first section of this program is designed to familiarize you with the Paylomatic drive system, its components, and their location. The second section provides a systematic procedure for isolating and correcting specific operational problems. Because the H-25B incorporates the basic Paylomatic drive system, it will be discussed first. The HAH-F system is essentially the same as the H-25B, but has additional components and will be covered later. These are the major components of the H-25B Paylomatic system. The Paylomatic system uses hydraulic oil flow to drive the machine, replacing the conventional torque converter and transmission. The Paylomatic drive incorporates two major systems, hydraulic and electrical. Hydraulic components include the reservoir, transmission pump, transmission control valve, drive motor, oil cooler, and filter. The solenoid valve is the link between the hydraulic and electrical systems. Looking at the hydraulic components in detail, notice that the reservoir is located directly behind the operator's compartment and is covered with a protective cowl. The reservoir is a closed pressure-sealed tank containing about 6 gallons of hydraulic oil, which supplies the drive system and the loader and steering systems. The cover on top of the reservoir provides access for cleaning the pump inlet strainer. The threaded fill cap and dipstick protrudes up through the protective cowl. The pump inlet strainer filters hydraulic oil as it flows from the reservoir to the pumps. The vacuum valve prevents reservoir pressure from falling below atmospheric pressure. If reservoir pressure drops, the valve will open and filtered air will enter the reservoir. It's important to remember that the inlet strainer and the vacuum valve filter must be kept clean to ensure oil flow to the pumps. The pressure relief valve on the side of the reservoir maintains tank pressure at 15 to 30 psi. The cooler circuit relief valve eliminates back pressure in the cooling system when the oil is cold. This valve opens when cooling circuit pressure rises to 125 psi. The transmission pump supplies oil for the drive system. This dual element vane pump is mounted to an adapter plate on the flywheel housing and is driven directly by the flywheel through a splined hub. This cutaway view of the transmission pump shows the location of the two pumping elements. The small element delivers oil through the transmission control valve to the drive motor whenever the drive system is engaged. Flow from the large element is directed to the motor only when pressure in the drive system is below 750 to 800 psi, and the shift lever is in the F2 or R2 position. Thus, oil flow from the large element is used only for high-speed operation. Notice also that this pump incorporates intravanes. These intravanes are located at the bottom center of each vane to keep the vanes in constant contact with the pumping ring. The transmission control valve is mounted on the left side of the main frame under the operator's seat. This valve receives oil flow from the pump and directs it to the drive motor as determined by the gear selected and by the pressure in the drive system. The control valve houses 4 major groups of components. The control spool determines machine direction and speed by channeling the proper amount of oil to either the forward or reverse side of the drive motor. The spool, controlled through linkage by the shift lever, has 5 positions: forward high, forward low, neutral, reverse low, and reverse high. The high-pressure piston is located near the top of the valve. Piston movement is controlled by oil directed through the solenoid valve and then to the back side of the piston. This oil pressure pushes the piston against a heavy spring, which in turn pushes against the main relief valve and holds it tightly in the closed position. The drive system will not operate unless the relief valve is held closed by the high-pressure piston. The main relief valve limits maximum pressure in the drive system to 2,400 to 2,600 psi. Excess pressure causes the valve to overcome the force exerted by the spring and high-pressure piston. With the relief valve open, excess system pressure is relieved. The relief valve pressure setting is controlled by shims placed between the spring and high-pressure piston. Each shim added increases the relief valve setting by approximately 100 psi. The unloading valve and poppet control automatic upshift and downshift of the drive system when the control spool is in either the F2 or R2 position. The unloading valve poppet is held closed by a shim-adjusted spring. When oil pressure above 750 to 800 psi is directed against the poppet face, the poppet opens and oil flows to the unloading valve. Pressure of this oil on the unloading valve opens the valve and prevents oil flow from the large pump element from reaching the drive motor, thus an automatic downshift. When system pressure drops below 750 to 800 psi, the poppet closes, allowing the unloading valve to close, and an automatic upshift occurs as large element flow reaches the drive motor. The mixing valve remains open at pressures below 750 to 800 psi to allow large element and small element flow to combine for high-speed operation. Two anti-cavitation check poppets, one for each, the forward and reverse circuits, assure that the drive motor is charged with oil if motor speed exceeds pump speed. This condition could occur during fast deceleration or coasting. The drive motor is mounted to a frame crossmember just behind the differential and is connected to the differential with a drive shaft. The motor, driven by oil flow from the transmission pump, transmits power to the drive axle. The amount of resistance encountered by the oil at the drive motor determines drive system pressure. The drive motor is a reversible, single cartridge, vane-type hydraulic motor. The cartridge consists of a rotor splined to the shaft with spring-loaded vanes inserted into slots in the rotor and riding inside a stationary, elliptically shaped ring. An oil-to-air cooler is mounted just behind the engine radiator. Hydraulic oil, leaving the loader and steering cylinders, flows through the cooler, is filtered, and is then directed to the intake side of the transmission pump. Thus, the transmission pump is constantly supplied with cool, filtered oil. The drive system filter, responsible for filtering the oil as it passes from the cooler to the transmission pump, is mounted to the right side of the machine frame. The filter uses a 1/2 micron pleated paper element. The electrical system for the Paylomatic drive consists of the solenoid valve, micro switch, and brake pressure switch. The solenoid valve, mounted to the pump inlet manifold, is the link between hydraulic and electrical systems of the Paylomatic drive. The solenoid valve disconnects the drive when the accelerator is released or the brake pedal depressed. When the drive system is engaged, the solenoid coil is not activated, and the plunger is held closed by spring pressure. With the plunger closed, 1/10 gallon of oil per minute is allowed to flow to the high-pressure piston in the control valve. If the accelerator pedal is released or the brake pedal applied, the coil is energized, the plunger opens, and oil flow is exhausted through the pump manifold port. With no oil flow from the solenoid to the high-pressure piston, the main relief valve opens slightly, and system pressure drops below 150 psi, which is insufficient pressure to drive the machine. The micro switch on the H-25B is bracket mounted to the carburetor The function of the micro switch is to energize the solenoid, thus deactivating the drive system when engine speed drops below 900 RPM. When the switch is closed, the transmission disconnect indicator on the dash will light. The brake pressure switch located in the hydraulic brake line on the left side of the machine energizes the solenoid and thus deactivates the drive system when the brake pedal is depressed. When this switch is closed, the disconnect indicator on the dash will light. This completes the general discussion of the H-25B Paylomatic drive system. The HAH-F Paylomatic system is basically the same as the H-25 system. However, one major difference does exist. Under certain conditions, the HAH drive system utilizes oil flow from the loader circuit. Use of this loader circuit flow gives the HAH-F higher speeds than the 25B by providing increased flow to the drive motor. However, before discussing this feature of the HAH drive system, let us first review in general the location of the basic components. The reservoir is similar to that on the H-25B and is in the same location, behind the operator's compartment. The transmission pump is identical to the H-25's and is driven directly from the engine flywheel. The drive motor, again, is identical to the 25's, but the HAH-F incorporates a gearbox between the drive shaft and the differential. The solenoid valve, oil cooler, and drive system filter are identical in type and placement for the HAH-F and H-25B. But notice also that the loader control valve, an unloading valve, and a shutoff valve are incorporated in the HAH-F drive system. The HAH-F transmission control valve is mounted on the right side of the machine frame under the operator's seat. The valve is identical to that used on the H-25, except the control spool is inserted from the opposite end of the valve body. The micro switch is mounted inside and near the front of the operator's compartment. The switch is activated by a lever on the accelerator linkage cross shaft. The purpose of the micro switch is, again, to disconnect the drive system when engine speed drops below 1,000 RPM. When this switch is closed, the transmission disconnect indicator on the dash will light. The brake pressure switch is located in a T at the brake master cylinder under the front floorboard. This switch disconnects drive when the brake pedal is depressed and when closed, lights the indicator on the dash. This system schematic illustrates the additional components in the HAH-F drive system: the loader control valve, unloading valve, shutoff valve, and related piping. These components automatically channel oil flow from the loader pump into the drive system when the boom and bucket circuits are not activated and the drive system pressure is between 0 and 1,300 psi. Loader pump flow is utilized under these conditions to give higher ground speeds than in the H-25B. The loader pump is mounted to a bracket at the fan end of the engine and is driven directly by the crankshaft through a coupling. The loader pump is a dual element, external gear type pump. The large element supplies the loader circuit and the small element supplies the steering circuit. The loader pump unloading valve is mounted to the same frame crossmember as the drive motor. This valve automatically directs loader pump output to the drive system when system pressure is below 1,300 psi. At pressures above 1,300 psi, this valve exhausts loader flow to the reservoir. A shutoff valve, located on the right-hand panel of the operator's compartment, permits the operator to manually override the automatic unloading valve. In certain operating conditions, short cycles or up and down ramps, for example, the machine is continually working near the 1300 psi pressure range. Under these conditions, the unloading valve would continually kick loader pump flow in and out of the drive system. To avoid this intermittent flow to the drive system, the shutoff valve can be closed and all loader pump flow is exhausted to reservoir. In addition to the half-micron drive system filter, the HAH-F incorporates a second filter to clean the loader pump oil as it flows between the loader control valve and the unloading valve. This completes the general introduction section of the program. Part 2 will cover diagnoses of operational problems.